So, today we will discuss the space LP x mu, where x is an arbitrary set and mu is a measure on it. Now, this space LP consists of the measurable functions which are pth integrable. So, in fact, it requires the knowledge of the little bit about the measure theory. What are the measurable functions? What is the measure? How to introduce the concept of the sigma algebra? All these things we will require to introduce this. In fact, before going, let us see the concepts which are needed for this space to be discussed. The first concept which we wanted to introduce is the Lebesgue measure, Lebesgue outer measure and Lebesgue measure. Lebesgue outer measure. Now, here we will deal all the sets, whatever we deal, they lie in a real line, or they are the part of the real line or real line R. So, when we say the interval a b, whether it is a semi closed interval or closed interval, or maybe half closed and open interval like this, then the length of the interval is nothing but the difference between b minus a. Now, if the set A is the set of points on the real line, but they are scattered point. Say this is real line or points are somewhere here like this. So, collection of these points is suppose A. We wanted to know the corresponding length of this or the measure of this set A. So, the idea of the measure is the generalization of the concept of the length of an interval, whether it is open, closed or semi closed interval. So, in order to get the measure of the set A, we introduce first the concept of the Lebesgue outer measure, and then slowly we will go for the measure for this set. So, what we do is here that the outer measure, we define the Lebesgue outer measure of a set H follows the Lebesgue outer measure or simply an outer measure of a set A, of a set say A, which is a part of a real line. Set A is defined as mu star, let it be mu star A is the infimum of sigma length of I n is 1 to infinity, where the infimum is taking over over all finite or countable collections of intervals I n, which is of the form say A n B n type, this type A n B n type, such that the countable union of this, I n's covers A. such that countable union of this one covers it. Okay. So, what we do is we are enclosing the points of the set A by means of the intervals I 1, I 2, I n and so on, finding out the length of these intervals, taking the sum, then change the length of intervals again I 1, I 2 is replaced by I 1 days, I 2 days, etc., and again find out the sum of the length of this, choose the infimum value where infimum is taken over all such possible intervals. Then if this infimum exists, we say it is the outer measure of the set A. Okay. Now, this outer measure satisfies the following conditions. The result is, or theorem, the outer measure mu star of A will always be non-negative. The outer measure of an empty set is 0. Outer measure of a set A is less than equal to outer measure of a set B if A is contained in B. This always be satisfied. Now, this outer measure is not a additive function. In fact, it is a sub-additive function. The outer measure is not additive. Even countably finitely additive is not there. For example, if we take this set X as a set of X as the set of 100 points arranged in 10 columns, such that each column has 10 points. Each column has 10 points. With each column 10 points, and let us suppose H is the power set of X, class of all the subsets of X. Define mu star of E as the number of the columns which contains at least one point of E, which contain at least one point of E, where E is an element of H. Okay. E is an element of H. Now, this mu star E clearly satisfy this condition. Mu star A is greater than equal to 0, mu star phi will be 0, mu star A is contained in mu star B and so on. So, this is an outer, this satisfy the all the three conditions, but we claim that mu star is not finitely additive function, because if we choose the two sets E 1 and E 2, let E 1 is suppose x 1, x 2, x 3, x 4, E 2 is suppose this is, suppose these are the 10 columns. Okay. So, E 1 element lying here x 1, x 2, x 3, say x 4, and E 2 is suppose x 5, x 6, x 7, where the x 5 is here, x 6 is here, x 7 is somewhere here, okay, and x8 let it be here. Okay. So, these are the some 10 columns where the elements E1 and E2 lies in this column. Now, if we take the mu star of E1, then mu star of E1 has occupied basically 3 columns 1, 2 and 3, because x1, x2, x3, x4 lies in 3 columns. So, this is 3 mu star of E2, the elements x5, x6, x7, it lies between 1, 2 and 3, 4. So, this is the 4 columns are required to cover the element of this. If I take the E1 union E2, then what we get is E1 union E2 is x1, x2, x3, x4, x5, x6, x7, x8, and the intersection is empty, because the x1, x2, xn they are different elements. These are all different, xi is not equal to xj. So, if we take this, then E1 intersection E2 is empty, they are disjoints, and E1 union E2 requires 1, 2, 3, 4 and 5 columns. So, measure of this, outer measure of this is E1 intersection this is 0, while the M E1 union E2 is 5, which is not equal to the mu star of E1 plus mu star of E2. Rather than it is strictly less than, this value. So, in spite of the E1 E2 are disjoint, the mu star of E1 union E2 is not equal to the mu star E1 plus mu star E2. This shows that mu star is not finitely additive function. So, though we have introduced the concept of the outer measure, which is the Lebesgue outer measure, but this has a drawback that this is not a additive function. So, what we are interested in identifying those elements of X, those outer measures Lebesgue measurable functions, which decompose the each set in such that outer measure becomes additive, and those sets we call it to be a measurable sets. So, we define the measurable set the set E is Lebesgue measurable or simply a measurable set, Lebesgue measurable for each set A. If for each set A, we have M is mu star of A equal to mu star of A intersection E plus mu star of A intersection E complement. Okay. Then such a set E is said to be a Lebesgue measurable set. Okay. And the class of all Lebesgue measurable sets, Lebesgue measurable sets, we denote this by capital M, class of all Lebesgue measurable sets, and it is very easy to show that if a set whose outer measure is 0 then this set E is Lebesgue measurable sets, and this class of Lebesgue measurable sets forms a sigma algebra. The class M forms sigma algebra. What is the meaning of sigma algebra? We define the sigma algebra as a class of subsets of an arbitrary space X is said to be a sigma algebra if X belongs to the class and second one is if X belongs to the class and the class is closed under the formation of countable union and of complement, and the class is closed under the formation of countable unions and of complements. That is the meaning is that is a class is said to be a sigma algebra if A belongs to the class, say I am taking M here, B belongs to the class M, then A union B must be in M, A minus B must be in M, and not only this, if Ai's belongs to M, then countable union of Ai's I is 1 to infinity must be in M, and further the entire space X should also be in M. So, obviously, empty set phi is obviously in M. Now, it is easy to verify that empty sets, they are Lebesgue measurable sets, X is also Lebesgue measurable sets, okay. And if A, B are there, then A union B will be A minus B will be available in Lebesgue measurable sets and countable. So, Lebesgue measurable set, class of Lebesgue measurable set M is basically a sigma algebra. So, it is easy to verify. I am just I am not giving the complete proof. It is easy to verify that the class M of all Lebesgue measurable sets is sigma algebra. Okay. So, this concept we will require here, the concept of the sigma algebra. Now, as a remark we will just put it here. If E is a measurable set, then we write mu of E in place of mu star of E for the Lebesgue measure of E, for Lebesgue measure of E. That is our concept on the sigma algebra of measurable set. Okay. And this we use. Now, every interval is a measurable sets. So, there is nothing to here prove it. Let me take an example here. Suppose we consider the class X as a class of finite union of the interval of the form semi-closed interval A I B I. If we consider the class of finite union of A I B I, then it can be shown that it forms a sigma algebra. All these properties will be satisfied, and of course, mu of A I B I, that is the measure, we can write as B I minus A I. So, this is example we can get it and shown this forms the Lebesgue measurable, the algebra, sigma algebra of these sets. Now, there is another concept which we need it now, the concept of the measurable functions. I am going in very short, just reviewing the whole thing, because this is a separate discipline, okay, measure theory, where you will see in detail, but this terminology we will use in establishing capital LP as a Banach space, as a norm space. So, to show this one, we require these concepts of measurable function, integration of the pth integrable functions, and like this. Okay. So, that is why we require this. The measurable functions, let us introduce this measurable function as, let f be an extended real valued function defined on a measurable set E. Measurable set E. Then we say f is a Lebesgue measurable function, Lebesgue measurable function, or simply a measurable function, simply a measurable function, Lebesgue measurable function, or simply a measurable function if for each alpha belongs to R, R is a real, the set X such that f x is greater than alpha is measurable, is Lebesgue measurable, is measurable. So, what we see here is a function f is said to be a Lebesgue measurable function if the corresponding set, this set of those points where the f x is greater than alpha for each alpha is a measurable set. So, this set is a measurable means it decompose any other set into a two disjoint sets, so that the outer measure becomes additive. That is, if I take this set to be say E, then m star of A equal to m star of E, A intersection E plus m star of A intersection E complement. If it is satisfied m star or mu star, then this set will be a Lebesgue measurable set. So, in order to show the function to be Lebesgue measurable function, we have to show the corresponding set is a Lebesgue measurable set. And this definition is equivalent to the following conditions are equivalent. The following statements are equivalent. The first is that say f is a measurable function. It means this set is a Lebesgue measurable set, is measurable or Lebesgue measurable, it is okay. Second condition is that for every alpha belongs to R, the set where the f x is greater than or equal to alpha is a measurable set. Third is for every alpha belongs to R, the set X such that f x is strictly less than alpha is measurable set, and fourth is for every alpha belongs to R, the set X such that f x is less than equal to alpha is measurable set. So, all these conditions are equivalent. So, in order to test the function f to be measurable, we can prove any one of the set. If it comes out to be a Lebesgue measurable set, then the corresponding function will be a measurable function, Lebesgue measurable function. Further, it can be shown easily that if the function f is measurable, if f is measurable function, then the set of those point where the f x becomes constant alpha is also a measurable function, is a measurable function, is a measurable set. This is a measurable set for any extended real number alpha, for an extended real number alpha. So, even the set x where the f x becomes constant, these are all measurable sets if f is a measurable function. Every constant function is measurable. There are an example, the constant functions are measurable functions. Then the characteristic function chi of A, characteristic function, characteristic function of a set A is measurable if and only if A is measurable. This can be as shown. Okay. So, we are not continuous functions are measurable. Another examples are measurable functions. Similarly, satisfy the condition all the algebraic properties. Say if f and g are measurable, their addition, subtraction, f plus g, f minus g, f plus a constant g, these are all measurable functions. So, if f and g are measurable functions, then f plus minus g are measurable, f g are measurable, f plus c is measurable, c f is measurable, these are all measurable functions. Similarly, if a sequence f n is a sequence of measurable functions, then the limit superior f n, limit inferior of f n, supremum of f n, infimum of f n, these are all measurable functions. So, class of measurable functions is a very big class, and we wanted to make use of this class and introduce the concept of our LP space over this class. So, that is the then another concept which we need is almost everywhere. If a property holds, except on a set of measure 0, then we say that it holds almost everywhere. And we use the abbreviation A dot A. almost everywhere. Now, the result, one result we will make use. The result is, let f be a measurable function and let f equal to g almost everywhere. Then g is a measurable function. Means, if a function g which is equal to f almost everywhere, that is except the point where the function differs from g has, and that set forms a measure 0, then we say f equal to g almost everywhere. So, such a function g will also be measurable if f is measurable. So, any function which is equal to g almost everywhere, almost equal to a measurable function almost everywhere will be a measurable function, will be Lebesgue measurable function. Then another result which we need also, suppose f be a measurable function, then the positive part of f, which we denoted by f plus, and it is the value f x and 0, and the negative part of this, which is denoted as maximum of minus f x comma 0, then the positive and negative part, of f, this is the negative part of f. Both are measurable function. Positive and negative part. The advantage of writing this is that if f is any arbitrary function, then we can write it f as f plus minus f minus, and mod of f we can use it f plus f minus, and f plus and f minus both are non-negative, functions. Okay. So, we can make use of this. The another concept is essential supremum. If let f be a measurable function, then the infimum of alpha, where f is less than equal to alpha almost everywhere, is called the essential supremum of f, and we denote this by and is denoted by essential supremum of f, like this. Okay. Now, in this we have one or two results. The first result is, for any measurable function f will always be less than equal to essential supremum of f almost everywhere. This holds for any measurable function f. The second result which we require also, the essential supremum of the sum f plus g is less than equal to essential supremum of f plus essential supremum of g. The similarly, we can have a concept of the essential infimum concept, and that will be required. Okay. Now, once we have introduced the, then we require the concept of the integration. The concept of the integration is the integration of functions of a non-negative functions. Non-negative functions in very level. So, here first we will see the simple function. Simple function is a function non-negative finite valued, a non-negative finite valued function phi x, a non-negative finite valued function phi x, taking only a finite number of different values each called a simple function. Simple function is called a simple function. For example, a characteristic function chi. The chi of A has a value 0 and 1 only if x does not belongs to A, and when x belongs to A, the value is 1. So, such a function is a simple function, because it has only the finite number of values, that is only 2 values is having 0 and 1. Okay. So, in general, if suppose a 1, a 2, a n, these are the values are the distinct values taking by the function phi and suppose a I is the set of those points where the phi attains the values small a I. That is, we are separating out the point where the phi x attains the value a I. So, a 1 is the set of those points where the phi attains the value a 1, a 2 is the set of those points where the phi attains the value a 2, and like this. So, a 1, a 2, a n are distinct values, then we are getting the corresponding sets a 1, a 2, a n, which are also V disjoint sets. Okay. So, a 1, a 2, a n, these, hence phi can be written as, then phi of x can easily be written as in the form of the finite sum I is 1 to infinity a I characteristic function of a I x, because when x belongs to a I, the value of this comes out to 1 and only a I will be there, rest will be 0. So, when x belongs to this, phi of x is equal to a I, it coincide. So, phi x can be written as a finite sum of this in the form of the simple functions chi of a I, in form of the characteristic function, and this set a I, the set a I are measurable if phi is a measurable function. Because this, if you remember, we have already shown one result, that if phi is a measurable function, then the set of those points where phi attains the constant values will also be a measurable set. So, this set will be measurable if phi is a measurable function. So, a I is all measurable if phi is a measurable. So, now we take the integration, introduce that of a simple function, integration of the simple function phi. Okay. let phi be a measurable simple function then the integral of phi dx is defined as I is 1 to n a I into measure of a I, because a I is a measurable set. If phi is a measurable function, a I is a measurable set. So, measure of the set a I can be computed, and measure of a I, when multiply the corresponding values a I, take the summation, it will give the value of the integral phi dx over the range. Okay. So, where a I and a I is them, then this we call it as the integral of phi. Now, with the help of this simple function, we can now introduce the integral of a non-negative measurable function. So, integral of non-negative measurable functions. So, for any non-negative measurable function, f, for any non-negative measurable function f, the integral of f denoted as integral f dx is given by integral f dx is the supremum of integral phi dx, where the supremum is taken over all measurable simple functions. F measurable simple functions phi, such that phi are less than or equal to f. Means supremum is taken over all phi which are less than equal to f, or simple measurable function phi which are less than or equal to f. That is so, this is the way we introduce the concept of the integral, Lebesgue integral of the function f, when f is a non-negative measurable function. This we call it as a Lebesgue integral. Okay. Lebesgue integral of this. Now, if the function is defined over the set E, then for any measurable set E and any non-negative measurable function f and any non-negative measurable function f, the integral of E f over the set E denoted as integral f dx over the set E is nothing but integral of f into characteristic function E dx integral, and this is as good as our saying integral of f dx. So, we will say this is the supremum over psi, psi is less than equal to f into characteristic function of E integral of psi dx. Okay. So, this way we can introduce the concept of, and this integration we call it the Lebesgue integral of f over the set E. Lebesgue integral over the set E. Now, here we have taken the f to be a non-negative measurable functions. Now, if suppose f is not a non-negative measurable function, is a general function, then we introduce the Lebesgue integral of the general function h. The Lebesgue integral of general function. So, let f be a measurable function, f be a measurable function, need not be a non-negative, need not be non-negative, okay? Need not be a non-negative function, and if the positive part of this function is finite, negative part of this function is also finite, then we say that f is integrable, Lebesgue integrable, and the integral of f dx is integral f plus dx minus integral f minus dx. Now, both are non-negative, f plus and f minus both are non-negative. So, we can introduce this, we can write the integral f plus dx in terms of the supremum of a simple function. So, this can be written as a supremum of simple function, this can also be written as a supremum of simple function, hence integral of f will be well defined. Now, this even idea can be extended to an extended valued function, provided the one of them means it should not be infinity minus infinity, it should be well defined. Okay? So, except that point, otherwise those point where it has a ambiguity must have a measure 0. So, we get this. Okay. Now, this is all about this measure theory part, and with the help of this, now we can introduce the concept of our LP space. Okay. So, let us see now the concepts LP space, because this is very much required for introducing the concept of LP spaces. So, let x, s and mu this separate be a measure space, What do you mean by the measure space? That I will explain later, and p is greater than 0 and p. We define capital LP x mu or simply capital LP mu to be the class of measurable functions here. When we say the measurable means it is a Lebesgue measurable function. Okay. Functions f such that integral of mod f to the power p, the Lebesgue integral of mod f to the power p is finite. So, basically what we have, we are choosing those measurable functions which are pth integrable, that is the Lebesgue integral of power pth function mod f to the power p is finite, with the convention that any two functions equal almost everywhere, almost everywhere, equal almost everywhere, specify the same element of capital LP. What do you mean? It means that in the class LP, we are not choosing the functions. LP is a class of functions such that each class, in each class the elements are equal almost everywhere. Say for example, if we take the 0 element of LP mu, it means the class of those functions where f equal to 0 almost everywhere. Then such a class, the collection of this such class, we are denoting by LP. So, what we are doing is we are taking capital X as an arbitrary set, S is a sigma algebra which is generated by a power set of X, and mu is a measure on S. So, this triplet X S mu will be known as the measure space. So, when we take the measure space, let f be a function defined on S, okay, measurable sets, then this function measurable function, if it is pth integrable function, then we say this is an element of LP mu, means it belongs to one of the class of the L. So, because LP mu is the collection of the classes. Say if I introduce the concept of the equivalence relation, the two element f and g are equivalent when f equal to g almost everywhere, f is related to g almost everywhere, then this will give the decompose the whole class into equivalence classes. That is if we introduce this concept of the equivalence classes, okay, that is if we introduce the concept of equivalence classes on f, on the class f, that is a class of functions, that is f is equal to g almost everywhere, that is f is related to g. If f is equal to g almost everywhere, then it will decompose the entire class into disjoint classes, okay, and these classes will form the LP space. So, we will discuss it later on after next. Okay, thank you very much.